I will show obviously some results, and maybe at the end I will say a few words about who we are, depending on the time. Robert was kind enough to say that we can include a demo in the presentation. I prefer an open discussion here, but if there would not be open discussion, we may have time for a demo as well to show. So this is the theory behind what we as a company stand for. So suppose the person who wants to write down quantum algorithm, quantum application, whatever they need, they just want to have it. An implementation space can be quite large. Implementation space, I mean the code that the quantum computer will actually execute. So the technology or automation that we see today is some sort of, sometimes it's called transpilation, sometimes it's called compilation, but from low level to low level. This is what we see today across the board. There is some speech about going from high level to low level in true fashion, as this was actually discussed long ago in the quantum arena. Q-Sharp had this agenda, but it was never implemented in the right way and so on. So going from low level to low level, you have a very low view from a mathematical point of view, a very low legal view of where you can go, because you must abide by the low level that you get. You don't know of the intended function of this low level code. Whereas going from a high level intention, telescopically, step by step into the low level, allows you the true flexibility which the user requires. Transpiler, even what is called today compilers, would never take this picture into this picture without knowing that a few of the qubits here are auxiliary qubits, in fact. And there is no technology beyond what we are now developing which will actually take you from a functional model that is represented here into an equivalent functional model that is represented here in an automatic way, without the user specifying in advance what auxiliaries are used. So this is just one example. I will describe more examples of this. So there are two pillars of going from a high-level description by technology into low-level implementation. First is that we really need to identify the modeling constructs, and we heard this in the previous talks, whether it is a simple for loop or whether it is more complicated idioms used by any quantum algorithms. If we identify the modeling constructs, then the compiler, the technology, has the ability, the knowledge to deal with those constructs in a reasonable way. So there is no embarrassment. One should not shy away from understanding what do real quantum algorithms actually need. And the second, of course, is the technology of understanding those constructs and implementing them under the specific constraints that are in enforcement now. Now, we see and hear this, I'm very happy, in the last very short time, last maybe 1 year, 2 years, not much more, we see many implementations of Shor's algorithm because people are starting to think this way. Up to until 2 or 3 years, there was no serious attempt or ability to actually implement the Shor algorithm. Now, not many people ask themselves why. The Shor algorithm is very, very simple. It is only 3 building blocks, which are all very simple. The Hadamard transform, by the way, Bettina mentioned the for loop around the Hadamard. You should not think of it as many H's over many qubits. You should think of it as a single function, a Hadamard transform, and this is what you would see in the classic platform, just a Hadamard transform, no for loops over there. Then a controlled modular exponentiation. This is completely classical in a sense. Modular exponentiation, and then the quantum part of inverse Fourier transform. Still, there was no implementation because this part here of a controlled modular exponentiation, people thought about it a lot. They wrote papers about it. We will see a few papers, but it was and is extremely difficult to implement, and people did not invest in this effort. And this is what we are here for. This is one example of identifying the constructs of how to implement this efficiently, and then using automation. So this would continue. I could share this presentation if anyone is interested. And then the first part of our work is to go over, the corpus of knowledge of quantum algorithms and understand what are the quantum idioms. What do people really need in order to implement on paper a quantum algorithm? So we identify some simple stuff like this sliding control structure, which you all identify. Sorry. And this is, Bettina mentioned the for loop overagent, so this is another idiom of gates, sometimes the same gates, sometimes different gates on 2 bits. And then some more complex structures, which appear in many algorithms. So a cascade here or a slide, but with a secondary structure. And more idioms such as those, and we implement those idioms in the modeling language. And then the modeling language on one hand allows the person or the algorithm developer to use those idioms in a simple way, and also without even any compilation can allow them, I would say, communication between 2 experts in a simple way where they both understand the language. But more importantly, from the perspective of this workshop or this conference, is to allow the automation unit to understand those idioms. It allows the developers to invest a lot of time on optimizing those idioms under constraints and create telescopically this Shor's algorithm structure. So this is somewhere in the middle of the flow from the simple Shor presentation or description of 3 building blocks down to the bottom. This is somewhere in the middle. So this is actually a real picture from a previous version of the classic platform. Today it looks nicer, but this is actually something that our user can actually write, and the automation will understand this graphical language. So I want to present here how close it is to what the people actually write in LaTeX in a paper. So now all they have to do is actually write it graphically for the automation to understand. And I thought I would give you some more examples, but I see that I won't. So this would be a graphical description of one of the steps of the Shor's algorithm that the user can present. And this would be the textual description at the same level. So this is still not machine code. It is much, much higher than machine code. So the user can decide whether they want each, I would say this would be the period function, each function to write graphically or textually. And now I will start to present the technology. As I mentioned, there are 2 pillars. First, understanding the idioms that a quantum developer thinks with. And second, to develop or create the technology which will take those idioms or high-level description into low-level code, but not by transpiling to very similar low-level functionalities, but by understanding that what the user needs, what the developer needs, is to be functionally correct, and not to be correct on any bit and piece because they don't care about it. So this is what you need to have in mind when I will describe the technology or the automation. So let's start with examples, and As usual, when we learn by examples, we will start from the simple and gradually grow. So let's look at the most common working horse of quantum computation, which is the multi-controlled gate, in this case multi-controlled X. So this is the function. What the user cares about in this particular case is that this function will be implemented. It has 6 control bits and one target bit in this particular case. It can also be controlled on zeros or ones, it doesn't really matter. And this would be a particular implementation of this function. It actually uses no auxiliary qubits. So the same number of qubits in the physical implementation as in the logical description is what the user wants. It has 168 CNOT gates and the depth of 225 in terms of CNOT gates. I believe it is optimized. You cannot do better, as far as I recall. And this is a different implementation of the same function. This would be a 9-qubit master implementation of the same 7-qubit functional multi-control block. So here you trade off 2 additional auxiliary qubits if you have them for much less CNOT gates. There could be an 11-qubit master implementation, and so on and so forth. And in this particular case, anyone here coming from engineering, one of my other hats, by the way, I have so many hats because I'm just very older than you guys. When you reach my age, you will have at least as much expertise as me. So if we are looking from an engineering perspective, we just have a trade-off table, which is so common in any engineering EDA tooling. And we see that the machinery, that the automation, that the synthesis engine needs to trade off between the widths of the function in any particular point in the algorithm. I did not tell you where this MCX is functionally located in the algorithm. So at any particular point, the synthesis engine needs to trade off between widths, number of available qubits, memory if you like. Actually, the auxiliary qubits, it would be just the same. The number of CNOT gates, depending if the gates are noisy, depending if it is 2-dimensional connectivity, so any CNOT gate would require many swaps or not. So the number of CNOT gates, the qubit depths, and this for any function. We can go on to many more to functions which are larger. You see the point here. So this was one example. Let's look at another